Spec was interpreted through this competitive adsorption model, where basically the exchange current density for electrodeposition for iron doesn't really change much, but when we have nickel and cobalt, is affected by the coadsorption of iron hydroxide on the surface, which blocks the sites for nickel and cobalt, and for that reason affects their deposition, and we talked about that. Now, I'm going to complicate a little bit further, not necessarily only for deposition, but in general for deposition of all these important cobalt, nickel, and iron and metals, because they have similar properties. So I'm going to talk about electrodeposition in terms of the stability of the electrochemical interface, and you will understand what it really means during the lecture. All right, so if you look at the potential scale, and here is the hydrogen. This is equilibrium potential scale, right? So this is equilibrium for hydrogen. With respect to the standard conditions, etc., it's 0. But then you look nickel, you look cobalt, and you look iron. They are all on the left side of hydrogen. What that really means is that if I'm trying to deposit nickel and applying some overpotential for nickel deposition, at the same time I'm applying overpotential for hydrogen reduction or hydrogen evolution reaction, okay? And basically the same applies for cobalt, for iron, etc. Okay? So what that really in general means, as we discussed last time when we talked about specific metals, is that the efficiency of the current is generally less than 1. Basically what that really means, if you measure the current of the related to electrodeposition, let's say you think it is 1 amp, because you have concurrent reaction going on, actually 1 amp per centimeter square, for example, is not entirely related to nickel, cobalt, or iron reduction, but part of that current is related to hydrogen evolution or hydrogen reduction. And so for that reason, this gamma, which is current efficiency coefficient, is less than 1, right? Now, that's not necessarily a big deal, but when you talk about iron, cobalt, nickel, and similar metals, the problem is this. If you look Pourbet diagram, what you're going to see commonly for these three metals, is that there's a region of, let's say, metal stability, and this is the region of metal-iron stability, and then there's a region here which usually has some different types of things, but here you can see that there is a metal OH and part stability. What that really means is that metal is in equilibrium with the phase which is the precipitate of the hydroxide, and this is typically insoluble. All right, and what that really means is we discussed, if you're going to do any electrodeposition, we're going to do it for pH which is usually less than 6 or 5 and so on. So we want to be in this region where directly we have the equilibrium, or basically relation between metal ions, direct reduction to metal deposit. We move further on, then the situation is more complicated. Okay, and for that reason, there is some consequences. Even if we think we are at this pH, and we think we should get this reaction, as you will see, we might be actually here. And this is what I'm going to actually discuss, because those things nobody teaches you, and those are relatively simple things you need to know about, because not knowing about is a problem. And where this is really important is when we talk about iron, cobalt, nickel, also chromium electrodeposition. You know, it could happen even when you talk about copper and some other metals, but these are really essentially super sensitive to this type of the things that we're going to talk about, right? And so, since this is really technologically important type of the electrodeposition, where we either talk about nickel, cobalt, iron, or maybe chromium here, or we talk about alloys and so on, it always does apply, and you have to be aware of these fundamental important things. Okay, so the first thing is that current efficiency is rarely 1. Actually, it's not 1, it's less than 1. Because this happens in parallel with metal deposition. That's number 1. Number 2, and I assume everybody is familiar with chemistry to reasonable extent, the pH at the interface is not the same at the pH in the bulk. pH is representative or negative logarithm of the concentration of hydrogen plus ions in the solution. For that very reason, if you think your pH here, which is the bulk pH, when you do electrodeposition, actually your interfacial pH could be here. And for that very simple effect, because you're depleting hydrogen ions at the interface due to this reaction, you might be dealing with a problem that you're not aware of. And that's what I want to discuss today with you, and eventually next class we're going to have some extrapolation of this, right? Okay. So, if you heard about pH, you probably heard about pOH, and that same thing applies, that pOH at the interface is not the same as the pOH at the bulk. And again, pOH, which is negative logarithm of OH minus concentration, because of what I just said. Another thing that you need to keep in mind, which is the fundamental property of the water, there's an ionic product of water. I'm going to call this Kw. And that is equal to H plus times OH minus, and that is equal to 10 to the minus 14. And it does have small variation of the temperature, but let's assume this number applies all the time. That's called ionic product of water. What it really tells you is that there's an equilibrium in the water between ionized species, H plus, OH minus. And whatever the pH is it very low, very high, the product of H plus times OH minus has to be 10 to the minus 14. Now, what that really means, let's say you have pH 1, pH 1 basically means this is 1. What should be OH minus? 10 to the minus 14. Okay, so you can see if pH of the solution is very low or concentration of hydrogen plus is very high, then OH minus has to be very low. But this has to be satisfied no matter what. Okay, very important. All right. There's another thing very important, which is also, again, a fundamental thing. I'm going to call this number 4. And this is product Kp of solubility. Now, product of solubility applies for salts, for whatever. What I'm going to talk about today, really what's really important is for us, within the light of this discussion, is product of the solubility of hydroxides. Now, iron, cobalt, nickel, for example, if they're in their oxidation state 2, form nickel hydroxide, cobalt hydroxide, and iron hydroxide. And these hydroxides are solid. Okay? Another important thing is that iron in particular also creates iron 3 hydroxide, where the oxidation state of iron is 3 plus. And I'm going to address this most likely next class. But for today, I'm trying to generalize, and let's assume this is where we focus today on. Now, what that really means, if you think about product of solubility, is very simple thing. And if you refresh your general chemistry, is that, let's say I have some precipitate of metal hydroxide, and it's in equilibrium with its ions in the solution, which is Mn plus, and here is OH minus. And equilibrium means that it's dynamic equilibrium. What that really means that at the same rate, two things occur: dissolution of the hydroxide and reprecipitation of the hydroxide. That's dynamic equilibrium. But the rates are the same, so in net conditions, what you really see is nothing. But both the reactions occur at the same rate, right? Now, this equilibrium is defined in the simple way by product of solubility. All right, let me explain what is this. This is equal to Mn plus concentration times OH minus concentration on N. And N usually is equal to the oxidation state of the metal ion. So in this particular case, if you're going to generalize, it should be 2. But I'm going to keep N, because for iron 3, hydroxide is 3. So N is generalized description. And that is equal to some number. And these numbers uploaded, they're available in the literature, and usually they're presented as a ln or log of the Kp. So in literature you might have log of Kp, which is not far from knowing Kp overall. And obviously, if basically this is minus log Kp, the bigger the number, the less soluble hydroxide is. Okay, now let me give you an example. Iron 3 hydroxide, product of solubility is about 10 to the minus 34. So think about this. This is iron 3 hydroxide, and let's say if this is pH 10 on power 3, because N is 3 is 30, that means if there's an iron 3 ion present in a solution of order of 10 to the minus 4, I'm going to exceed this number, Kp, and what that really means, I'm going to be precipitating hydroxide. If I'm below this number, I'm okay. I still will have a soluble phase. The problem for us starts when we have conditions where this product here exceeds this solubility product number, right? And this is one of the lowest solubility hydroxide. Usually these are of order, and I'm not, they're not the same number, but they're order of 10 to the minus 20 plus, right? So there's a 10 orders of magnitude difference between solubility of this one and this one. Okay, so you just keep this in mind. All right, so why I'm telling you all this? Because when you do electrodeposition, it's not always getting metal ions into the metallic form. Sometimes you get complications because the interfacial pH is not the same as the one at the bulk because of this reaction going on in parallel. What happens is that you could, exceed product of solubility of hydroxide, and what would happen is that while you're depositing while you're creating your deposit, metallic deposit, you can co-precipitating hydroxide on the surface. And what that really means is that you're getting a mix of metal phase, which for this are either BCC or HCP or FCC, plus some oxide in there. And if you do XPS or EDS analysis, you're going to realize, wow, I have a lot of oxide in my deposit. So your deposit is not acting like a pure metal. What does it affect? It affects magnetic properties, coercivity, magnetic moment, hardness, stress, all sorts of stuff. So you have to be aware that electrodeposition not necessarily always produce the pure metal deposit, but in particular when your metal has the equilibrium potential on the left side of the hydrogen, it does creates opportunity for the situation where you can have co-precipitation of insoluble hydroxide at the electrode surface while you're growing the metal film. And that means metal film is not pure. And that means property of the metal film as compared to the bulk metal that we know in literature, tabulated properties, is not going to be the same. That is why I'm teaching you this today, so you understand the complications, right? Okay, so any questions with respect to this? This is Mickey Mouse stuff from general chemistry. Yes?
So, if you dissolve something like copper sulfate, and so would it form like copper ions or ions equivalent to this part of solubility? In the reverse case, if you dissolve something like ferrous hydroxide,
right,
it form equivalent to the part of solubility ions.
So you talk about you have copper ions and iron ions.
Yeah, if you dissolve like any hydroxide compound.
Yes.
Would it separate into like let's say iron and hydroxide ions, such that the product of their concentration is equal to this value?
So it depends how much you dissolve. If you're below the product of solubility, it's going to be soluble. But if you exceed it, it's going to start precipitating. Do you understand? Depends on the value of this product. So if the metal concentration times OH on N is bigger than Kp, you have precipitation. If it's less, then you have soluble. So you have to understand, it depends where you are with respect to the product. Product of solubility is some number that we know what it is. It's a function of temperature, but let's not discuss that, right? We know we can find this in the literature for many different insoluble salts, hydroxide, etc. Right? Okay. Okay, so now let's become a little bit more quantitative. No, the deposit itself is not pure metal, that's number one. It has a lot of hydroxide incorporated in there. That hydroxide itself is basically creating a phase mixture between metallic part and oxide part. That could be sometimes beneficial. I'll show you some examples. But generally, it could be also a problem because the fracture toughness of the deposit might be different, because usually this hydroxide precipitates at the grade boundaries. Grade boundaries become sensitized. That means that they are weaker, and that means that the deposit, the films itself are not so tough, and they might be cracking. For example, it might be, for example, if you're talking about magnetic materials, saturation magnetization for the metal phase is 2.4 Tesla, for oxide phase is probably 0. Now, for the volume of the film, that means your magnetic moment will be diluted for the percentage of the phase that is oxide you have in there. And you think you're generating film in a device that's supposed to do the job at 2.4 Tesla magnetization, but actually the real magnetization in that volume of magnetic material in our device is maybe 1.6. And so on and so on. So this is the tricky part, and generally this is all derived from the fundamentals, which we're going to talk about, but nobody tells you about this. And why nobody tells you? Because people either try to hide the truth from people. I told you the electrodeposition has been anecdotal science for a long time, and people who knew a lot didn't really have an interest of teaching others, because it's been a science confined to the metal shops, where they can do better than the other ones, and they don't want to reveal their secrets. And so the bottom line is this, knowing what we are talking about here, there's no secrets anymore. This is all well established. And so one of the examples is what we're going to talk about. All right, so let's start with our standard electrode solution. And this is an interface. And so this is H plus bulk. And this is H plus at the interface. And if I think about generating a diagram where this is H plus and this is some delta, this will be basically diffusion layer thickness. There will be a gradient in concentration of hydrogen plus ions as we go from the bulk through the diffusion layer to the electrode surface. There will be also, this is metal concentration in the bulk, and there will be metal concentration at the interface. Why? Because the metal ions are also transferred to the diffusion layer, and they're deposited, so they're depleted at the interface. Hydrogen ions are transferred from the bulk to the interface, and they're evolving as hydrogen gas, and that means they're depleted. So the bottom line is this: metal ions at interface concentration is not the same as metal ions in the bulk, and we discussed that, already. And hydrogen plus ions at the interface are not the same concentration in hydrogen plus ions in the bulk. All right, let's think about Fick's first law of diffusion about this statement. Obviously, if I'm describing the metal ion deposition, the flux of metal ions is basically given by the gamma, which is the current efficiency, current, divided by NF, which is the number of or oxidation state of the ion, Faraday's constant, right? That's equal to flux, and we know that this is equal to D metal ions diffusivity times Mn plus bulk minus Mn plus at interface divided by delta, right? That's something we already covered if you look back. For the hydrogen ions, there will be a flux as well. And this flux I'm going to write here is 1 minus gamma, because now the portion of the current related to the hydrogen evolution is not gamma I, but 1 minus gamma I, what is left, right? I. And for hydrogen, N is equal 1, so divided by F is equal to DH plus times hydrogen plus at the bulk minus hydrogen plus at interface divided by delta, right? We're just restating the first law of diffusion, hydrogen. Whether it's a metal or hydrogen, it doesn't really matter. Out of this, we should recognize, obviously, that unless we are at the diffusion limited regime where this dropped to 0, you know, this will have some value, right? Okay, that's very important. And you will see when we go through certain considerations, why is this important, right? Number one, it teaches you a simple thing, how to design your process in terms of the overpotential or the current that you want to use, where your ion concentrations, whether it's a hydrogen or metal, depending what we take as relevant, affects your decision-making process in terms of the process design. Usually, when we talk about nickel, cobalt, and iron, we can say that their concentration of order of 0.1 molar, right? It could be a little bit higher, a little bit lower, but that's about what we usually do. Now, to have some reasonable gamma, you want to keep the gamma of order of 0.1 or so. What that really means is that the concentration of hydrogen ions in the bulk is of order of 10 to the minus 2 to 10 to the minus 3 molar, right? So what you can see right now here is that this is 3, is that usually before you encounter any diffusion limitation for metal deposition, it's likely that you're going to encounter diffusion limitation for hydrogen evolution reaction, right? Okay, if you remember previously, I talked about these two concurrent reactions and voltammetry, and I show you iron and nickel in these examples. But what does this really mean, right? So if you have here current density, and this is potential. Actually, I should let me write this here. So if you have a current density, and this is potential, and let's say reversible potential is equilibrium potential is somewhere here. So I'm way more negative than equilibrium, so it's a large over potential. So I'm sweeping this way, right? At one point, you know, I'm going to have current going this way, and if I have no hydrogen coevolution, this would be how it looks like. This is diffusion limitations, and you know, basically it's a metal deposition. But because this equilibrium potential is more negative, the equilibrium potential for hydrogen, what I really see is this. Now this is diffusion limited current for 2H plus going to H2, and this is diffusion limited current for 2H plus going to H2 and to Mn plus Ne electrons is F. It's a sum of this diffusion limit current and for metal. So basically you can see this stepwise type of the process, right? So if I really apply somewhere here or here or here my equilibrium or over potential, right? I will be already in diffusion limited regime for hydrogen evolution, and I will be somewhere in activation control regime for my metal. And the bottom line is this. If we generalize, we're going to say that there will be some interfacial concentration of hydrogen and metal ions. They're different, but from them, one will be much lower. The one that is lower is the one we're going to focus on, because if this is very low, that means through the ionic product of water, Kw, now it also applies at the interface. I'm going to just say interface is equal to H plus at interface times OH minus at interface, and that is equal to 10 to the minus 14, right? So what that really means, let's say hydrogen is depleted, it's very low. If this is 10 to the minus 13, what is supposed to be? 0.1 mole. That 0.1 molar OH concentration near the surface is huge. And it's all product of this removal of H plus from the interface. Why is that bad? Because if, let's say, OH minus is 0.1 molar, and this is 10 to the minus 34, that means that the concentration of the iron 3 plus has to be 10 to the minus 30, and you're going to start seeing precipitation. 10 to the minus 30, you cannot even imagine how small number is that. But because you depleted so much hydrogen at the interface, locally pH is super large, super high. What that really means, OH concentration is large, 0.1 molar. But because this is so small, even it's power 3, it's 10 to minus power 0.1 times to power minus 3 is 10 to minus 3, it still means that iron 3 plus can be only 10 to the minus 30 molar, which is almost nothing. And you'll start seeing precipitation. Now that's the catch. That's how easy it is to get the problems. Now, obviously, since you know all of this, the idea is to teach you how to find the boundaries at which you can run your process without entering these very, very extreme conditions and getting deposit with a lot of oxide and stuff. Now, sometimes this is not avoidable. And sometimes you can expect to get deposit with a lot of oxide in there. There's nothing you can do about it. Now, there is some stuff you can do about this, and I can tell you later on, because there's a way to complex ions and do some stuff. But overall, there's sometimes things that you have to live with or try to mitigate, not necessarily exclude. What we're going to talk about here is how we can put some more analytics in this fundamental process going on. And then from there, figure out, for example, if I do pulse deposition, how long I'm going to pulse. Am I going to pulse to deplete metal ions on this interface or hydrogen ions? Because what's first to happen? If hydrogen is depleted first and starts to precipitate, because of that we precipitate hydroxide, I might grow my cobalt iron, which is going to have 30% of the oxide phase. That cobalt iron will not be good for any application because the magnetic moment will be disastrously low. When I was in Seagate, and I'm telling you personal experiences, cobalt iron, and probably like 50-50, right? To make story short, had magnetic moment at 2.4 Tesla. It's at room temperature. This is the highest saturation magnetization that you can achieve in any material, right? And because we needed so much field to write media that is of specific kind, this type of the alloys we grow with vacuum deposition. But it turns out it's very difficult to process, very slow, to make a story short, it's very hard and so on. And so we produce the same kind of materials with electrodeposition, which were super soft and so on and so on. But, again, that was related to the film. Now, when we grow devices, sometimes the resist, this dimension here, is only 20 nanometers. So it's not like open space where, you have mixing and you can reduce the diffusion layer thickness and improve the transport and so on. So what happened is that we were growing devices, but the device that is grown in this recess here, which is supposed to do the writing, has a magnetic field of 1.1 Tesla, while the rest of the film, which is open space type, had 2.4 Tesla. None of the devices work. And I haven't done that work, but when I realized, after a little bit thinking, I figured it out that we have to take care and calculate everything for this geometry, not for open film geometry, which is a little bit difficult. And if you're really curious, you can find this paper in my webpage. Why I'm telling you this? The difference between the company making money, profits, and making losses of a few $100 million is whether you are taking into account engineering calculation for this and this versus just applying a Dissonian science. Once we figured it out, this and this, Seagate had the best alloys in the business for 2 years, which means we were doing cheap production, electrodeposition, materials for great performance, while the rest of the competition could not catch up. Eventually they learned how to do it, but in 2 years you generate enough profits to return back into research and so on, to come up with a new product and so on. That's how you, in this high-tech business, you stay in business, by knowing ahead of time versus your competition, having a better product long enough to generate enough profits so you re-energize your research and come up with a new product before the competition catch up. And so once they catch up, you release a new product, which is better. And that game is typically, the turnover is between 2 and 4 years. That's why high-tech enterprise puts significant money into research. Because if you don't have a research, you don't have a better edge over the competition. If you don't have an edge over the competition, then it becomes manufacturing science. And that is who can make cheaper. And that means the salaries are freezed up and just basically go little by little, and the stock is more or less, But if it's an active field where the research is bringing newer and newer and newer things, every 2-3 years you're on top, bonuses, everything, and so on. So this is how you're supposed to understand this. Dinosaur technologies are the ones that really, there's nothing else to invent, there's nothing else to change, it's just who's going to make it cheaper. And those are typically shipped abroad, because obviously, salaries here are really high, and if you can teach somebody to do this exactly same thing, what he needs to do, and perfectly discipline, you don't need to do it here. You can ship it to someplace else. You just need the guy to make sure that it's executed properly. Right? But if this technology requires active research, that's what it is here, because this is a high gain, high salary, high money. So this is how it really works with the high tech. Okay. All right. So let's put a little bit more analytics to what we have discussed here. David, how we do with the time? All right. So let's create a balance here, which is basically gamma I over NF is equal to diffusivity of the metal ions times Mn bulk minus Mn at the interface divided by delta, right? And let's do the same thing for hydrogen, which is gamma times 1, it's 1 minus gamma times I. By the way, I is the current density, milliamp per centimeter square second. This is Faraday's constant. It's coulomb per mole. Okay, so everything else, this is centimeter square per second. This is centimeters, and these are mole per liter or mole per centimeter cube. Depends how you want to do it. All right. And if we talk about first Fick law for the hydrogen, then it's basically 1 minus gamma times I over, and N is the same N as it is here, as it is here, as it is here. And for hydrogen, this is just 1, so I'm going to just skip. And then this is DH plus times H plus at the bulk minus H plus at the interface divided by delta. Now, for your information, typical number for diffusivity of metal ions in the solution is of order of 5 times 10 to the minus 5 centimeters square per second, and typical diffusivity number at room temperature of hydrogen is about 1 times 10 to the minus 5 centimeters square per second. So you can see that metal ions are actually, I inverted this. It should be like this. It's 1 times 10 to the minus 5, and this is 5 times 10 to the minus 5. So you can see that hydrogen ions are faster diffusers than metal ions because they're smaller. That's all what it is. And you can come up with these calculations using the Nernst-Einstein equation. I don't want to talk about this because that's already becoming too much. But if you really want to know how to calculate diffusivity of metal ions, there's a Nernst-Einstein equation. You need to know viscosity of the water, diameter of the ion, KT, whatever, some small, and you can calculate these numbers relatively well by assuming the dimensions of the ions in the solution. Okay. Now the idea here is, knowing these two equations, is to basically come up with the value of metal ion concentration at the interface and H plus, right? So from this one, M plus, and the interface is equal to, now what you can put this under this, and then multiply this over this, and then you're going to have that this is equal to Mn plus at bulk minus, and then you're going to have gamma I times delta over NF times dm n plus. That's for the metal ions. This is concentration at the interface, this thing here. And then for hydrogen is a little bit or basically it's the same. It's going to be for hydrogen concentration at the interface, it's equal to H plus in the bulk minus, and you're going to have just the difference here is 1 minus gamma I delta over F times dH plus. So we can actually calculate this interfacial concentrations of metal ions and hydrogen by knowing the current efficiency, current density, diffusion layer thickness, diffusivity of hydrogen and metal ions in this solution. This is still really truly nothing new that you heard from me, assuming what we have discussed before, but I just tried to repackage this to guide you to a new form. And this is all what the good scientific discussion leads to. You start with some really common things, and then you start putting extra few guiding lines, and you're coming up with the new conclusion. So that's what we are actually doing here. All right. Now we have these calculations, which are important. But if you remember, when we were talking about Kp, which is the product of solubility, and general product of metal ion concentrations times OH minus concentration, is that instead of H plus concentration, I would like to have OH minus. What's the connection? The connection is this, right? So I can always write that OH minus concentrations, whether it's at the interface or in the bulk, it really doesn't matter, is equal to Kw, which we know is 10 to the minus 14, divided by H plus at the interface, because that ionic product of water always is satisfied regardless of the spatial position where we are looking at, right? So if I can calculate this, basically I can calculate that OH minus at the interface is equal to Kw, which we know it's 10 to the minus 14, divided by whole thing here. And to save the space, you see this, I'm just going to write H plus at interface, okay? Where H plus at interface is H bulk concentration minus this whole thing here, right? Okay, that's what we have. All right. So now it's kind of caveat. Why? Because nobody would tell you this. I tell you this because I want to teach you something, but in general, it's kind of interesting thing because you have a mathematical expression that is really interesting to analyze. And let me go and show you this, what I have in mind. So here I'm going to write metal ions concentration interface times OH minus at interface power n, okay? Here there will be different things. I'm going to write them as we discuss because that's the caveat of the whole lecture. This thing here, product, if I'm talking about product of solubility, it's a constant number. It's some kind of a number, and it doesn't depend on anything. It's Kp, right? Okay. Now, considering what we have shown here, product of the metal ions concentration at the interface, I'm just going to copy metal ion concentration in the interface is this. All right, so it's metal ion concentrations in the bulk minus gamma I delta over dm plus times and F multiplies this thing here, which is Kw, divided by this thing here, right? So Kw divided by H plus bulk minus 1 minus gamma I delta dH plus n is equal 1, so it's just F, right? Now, this is important thing. This product here is a function, for example, of the current. Current here is in the numerator, and here is in denominator, for example. It's also product of this gamma thing, and 1 minus gamma. Those are opposing terms. It's a product of delta here and delta here, but here is the denominator, here is the numerator. When you have mathematical expression where the same type of the parameter is opposing itself in a product, like here, what does it tell you is that there is an optimum. And how you define the optimum is up to you. Now, if our optimum is to be below Kp value, because above means precipitation, below means solubility, or metallic deposit, here we have crab, right? So, if I put here delta or current density or gamma, or even if I put here H plus bulk or metal concentration bulk, they all have an effect how this product is going to look like. Right, so to make a point is your homework I think number 3 is to take an arbitrary example. Let's say we've taken an example of nickel you can find in the literature what's the solubility product of nickel hydroxide, Kp for nickel hydroxide. And see how this product varies in terms of delta, current density, gamma, etc. What that really means, you fix everything and you just vary 1, right? Or you fix everything, you vary this, delta. Or you fix everything, you vary gamma. So, or you fix everything, you vary just metal ion concentration. Why I'm telling you this, which is really what you're going to learn from this homework. Usually you think that having high metal concentration in the solution is good. Yeah, that's a fact. You avoid diffusion limitations, dendritic growth and so on. But when it comes to precipitation of hydroxide, if this is really big, that means this affects, I mean, there will be effect of the depletion, but let's say to a smaller extent because this is much bigger. What that really means is that when you talk about product of solubility, this is big. Even for very small concentration here, you might be in jeopardy of exceeding this. Now that's counterintuitive with respect to what we talked about, because you think that metal concentration, the higher the better. Yeah, but depends in what kind of situation. So your homework really asks you to make these plots and see how all these variables for arbitrary numbers affect this. And you will see, interestingly enough, someplace you will see this, someplace you will see this, depending, the math is interesting here. This is what is your homework, to learn a little bit about these effects. Now, the next class, I will be more specific and discuss this situation as the worst case scenario, because this is one of the most insoluble hydroxide, and show you how does this affect magnetic moment, coercivity, this kind of stuff. But what you're really going to learn from this homework is really an optimum conditions with respect to different things, such as metal ion concentration, pH. For example, pH, obviously, the higher is this, right? The better, because you're not going to have much of the depletion. But the higher is this usually means this is very large too, low too, because you're pretty much going to be evolving hydrogen only, not metal deposition. That's usually not good, because you don't want to have dominant reaction, something that is not related to metal deposition. That means you're wasting energy producing hydrogen instead of doing metal deposition. Now, let's say in nanotechnology, not a big deal, but if you're doing nickel deposition, which is the factory size of this cluster times 50, where the nickel metallization happens and serious electrical energy goes into the process, you're actually very weary about current efficiency. The higher, the less energy you need to deposit certain thickness of the nickel, for example, right? So it depends on the application. But this is what I want you to do, to plot this kind of stuff and see how this really looks like. And again, you can use arbitrary numbers, just the idea here is that you can see opposing functionals, because here's I, and they multiply each other, right? And so it turns out it's going to depend on the values of this and so on and so on, right? This is what I want you to try for homework number 3. Okay, so I'm going to finish this lecture about interface stability next class. And then you're going to get midterm project. Now, the midterm project is going to be a little bit more complicated than homeworks. But it's not going to be something super difficult, but it's going to be something which is going to force you to really adopt the material, think about, what you're doing and so on. And if you need my help, you will have office hours and you can talk to me. You will have plenty of time. I think it's going to be probably more than 2 weeks or 3 weeks, something like that. So if you start thinking about this on time, it's likely that you're going to learn in the process and have a good midterm project. If you wait until 2 nights before the deadline, forget about it. The electrodeposition is not something you can get quickly. It's a complicated field. I tried to simplify it as much as I could, but you saw we talked about additive, adsorption, all this kind of stuff. This is all over the place. That's why there's very few people who are good in this. Being good in this means you have a really highly paid job. Anyway, I can tell you only one thing. There's no student I have produced in my group, PhD student, that has been without a job 6 months before its graduation. Here's an example sitting here. He already has a job. I have a hard time keeping him here because he has a job 1 year before, actually roughly 1 year before he graduates. Same was with Nikhil, which is I graduated this guy in December. He's already having jobs. Kamir, most of my students. You know why? Because the thing is, what you learn here, of course, you're not learning as much as my students because that's what they do for a living, and your guys are having just a course. But what you learn here is unlikely you're going to learn from any books on the way that I tell you, and it's unlikely that is going to be explained to the way that I explained to you in terms of comprehension is really digested, can be simplified more than what I say. If you try to learn this from the books, it's going to take way much longer time. Tomorrow you end up in a company and you have an idea about this versus the other engineers who have no clue. It could be the difference whether you keep the job or somebody gets laid off. In high tech, electrodeposition is everywhere. Everywhere. I mean, I cannot tell you how many examples there are. And so this is why I'm trying to teach you this in a way that it stays with you in terms of the reflex, where you understand fundamentals and you can extrapolate whatever the problem is. This is how I try to communicate this to you, right? Okay, so see you on Wednesday, okay?